welcome to this public examination in the Faculty of Science. So today, a candidate, Nitinder Mohan, will present his dissertation, Edge Computing Platforms and Protocols, and the opponent is Professor Abhishek Chandra from University of Minnesota in the US. As the custos appointed by the faculty, I declare this public examination open.
Good afternoon, ladies and gentlemen. Welcome to my introductory lecture for my thesis, which was titled Edge Computing Platforms and Protocols. This thesis presents several enabling platforms and protocols as solutions which would allow edge computing to function in the current environment. Before we get into understanding what the contribution of the thesis is, I would briefly try to give you an idea about what I mean by cloud computing, because edge computing can be considered an offering of cloud itself. So cloud computing has become the de facto way for application providers to deploy their services and cater to the users themselves. Essentially, the entire domain can be summarized as an interconnection of various data centers, and each data center has these various compute and storage capable servers which are arranged in racks, like the image that you see on the right there. These servers, they enjoy a very high capacity network fabric, and these data centers are also interconnected throughout the globe. There are many cloud providers that are operating in the world today. For example, your Google is Microsoft, and each one of them is responsible for handling and managing their own network. Essentially, the software that is running on these racks allow the developers to virtualize their resources and utilize the servers to the best of their capacities. In fact, more than 60% of the workloads that we see on the internet today is actually cloud-based. However, from the last few years, there is a new trend of applications that have been arising, and people are using this. These applications can also be termed as next generation applications. They also form the core of the upcoming buzzword, which is Internet of Things. These applications essentially require a lot of these sensors and cameras which are deployed in the environment, and they sense this information about users to get them to work. If you look about the trends of these applications in the next 5 years to come, we see that these applications are here to stay. In fact, they're going to increase their market share and they're going to increase that from the traditional data center-based applications. The number of sensors that are going to be deployed for these applications to function are going to increase until it reaches a value of about 7 sensors per every human being on this planet Earth. If you look into the requirements for processing such applications, we see that they impose 3 major requirements. Number one, they require very latency critical processing, which means that these processing needs to be done as fast as possible. This is essentially important for applications such as augmented reality and virtual reality, because this is guarded by the human reaction times, etc. The second requirement is that most of the data that is being generated by these sensors, which is also termed as big data, it needs to be aggregated and analyzed as soon as possible, because it can really affect your overall processing times of these applications. And some of these applications, for example, augmented reality, can have context and location aware requirements, which may change by user's position in the physical world itself. So the obvious question with these two domains is, can existing cloud that we see today, it can support these next generation applications? To answer this question, I will show the deployment of one of the major cloud providers, which is by Google. And these are all the data centers that you see deployed all over the globe. Looking at this image, we see an obvious problem here. The problem is that data center deployment is extremely skewed, and it does not follow the size of the continent or even the population density. Essentially, cloud providers, they deploy their data centers in areas which is likely to generate more money and profit margins for them. That is why continents which has more developed countries' densities that sees more data center deployments, for example, your North America and Europe. On the other hand, continents which are more developing countries have a little bit medium deployments, for example, Asia and South America. The worst hit is Africa, which has to route all the traffic for all the users that are running these applications to the nearest continent, which is Europe. And this is a problem for next generation applications, because most of the data that the sensors are generating and the cameras are capturing needs to be transported over the network, and this can really clog the network itself. And there's a very high transport cost that affects your overall latency for doing the computations. And this network latency is separate from the overall processing latency that these applications encounter in the cloud, and this has become a problem for these applications to function. That being said, this is the start for the new domain, which is known as the edge computing. And edge computing, like the name suggests, essentially means that these are small-scale servers which are deployed at the network edge. These sensors are not within the confinements of a data center, which are managed, but they can be in public infrastructures, and essentially they do what the data centers were having problem with, that is decrease the latency for doing computations now, because the data does not need to travel much further. This works for majority of IoT-based applications. Even for applications which require much more computations that needs to be done in the data center environment, edge servers can be very helpful because they end up reducing the network node by doing some pre-processing on the data that is generated by these sensors. And this removes the clog of the network that happens by transporting all of this data. Furthermore, these data centers, these edge servers, essentially they're very small in their fingerprint for deployments, so a lot of these servers can be deployed in the physical location, much closer to the user, and inherently they are able to support the location and contextual awareness requirements of these applications. So it seems like edge computing essentially answers to all the questions and requirements of the next generation applications, but is everything fine with the domain? And the answer is not really. It's because when you are moving away from the confinements of the data centers, which in an unmanaged environment, there is a lot of hardware, heterogeneous hardware that is around, and it is not able to support the quality of service requirements of the various of the users that are usually running their application on the cloud. Furthermore, the network itself is not a high bandwidth, high capacity network that is enjoyed by the cloud, because these servers operate in public infrastructure. So they will be using most of the time wireless, maybe public networks, which are prone to errors and latencies. Then there is also the problems of reliability, availability, and security of these servers, because they are not managed by a single entity anymore. The most important of them is that there is a significant lack of standardized protocols that would allow existing cloud applications to function on these edge servers. And this is where the thesis comes in. So we essentially try to look at how to enable the utilization of these servers to the best capabilities and abilities. For this, we take a look at how cloud computing came to be and how cloud computing became the giant that it is, what kind of protocols are operating in the cloud, and this can be summarized in the following service model. Essentially, all of the cloud protocols can be segregated based on what kind of applications they are catered towards, and there are different stakeholders which are operating for different layers, and they're only responsible for handling the particular usage and use cases. For example, your cloud providers like Google, Microsoft, and Amazon are only responsible for deploying these applications and tuning them or maintaining them. They also provide some softwares that would allow the best use of these servers in the infrastructure layers. But other than that, that's where their entire story ends. Softwares, for example, your Netflix and Ubers, they port their systems in such a way so that it can be deployed in these data centers. And they use public APIs to utilize the infrastructure of the cloud. The marrying part is the platform, where there are these very virtual machines and virtual containers that runs on these operating systems of the servers and allow these applications to scale as the requirements of the users increases. So if we extrapolate the service model of the cloud and we want to make it available for the edge, what kind of problems do we see here? And we see that edge computing essentially not only has to support the next generation application like factory automations and autonomous vehicles, but it also needs to support the existing cloud applications. Other than that, there is a whole lot of questions that exist in all the other layers, because who's now operating the hardware, who's running the hardware, is it still the cloud providers, or can there be your cellular providers and crowdsourced entities that can also be part of the picture? Similar to the infrastructure, it's no longer going to be homogeneous and maintained, so you can have your smartphones which have some processing capabilities part of this cloud, or you can have some specialized servers on the other hand, which works on the cloud, on the edge. Then your platform, you want to utilize existing systems for the cloud so that they're able to support the applications, but now your underlying servers are of very limited processing capabilities. So these existing protocols need to be able to get around that problems. So with that, this is what the thesis is contributing, and this is what we're trying to solve. So essentially, we're providing various protocols in every layer of this edge service model, which is catering to a particular problems or set of problems that exist in this space. For example, in the hardware, what we do is we provide a logical architecture of these edge servers that exist and would allow cloud providers to also deploy specialized servers in physical environments if they seem fit. And what is the best way to do that? We provide some protocols with that. In infrastructure layer, we are looking at how to best utilize the processing, network, and storage capabilities of these servers, and we provide various protocols and platforms for that. In the platform layer, we are looking at how existing virtual containers can be changed in the way that they can work on these unmanaged servers, and they can move around and provide the best kind of application requirements for the users. For this presentation, I'm only going to focus on these two solutions, which belong to the hardware and the infrastructure layer. And without further ado, I will first start to look into what is the hardware layer and overall answering the questions how to do computations on an edge cloud. So before we start designing any protocols for the edge, there is a need for a reference architecture that essentially allows a logical grouping for all of these servers that exist. And why this is important is because application providers need to know what is their application going to run on. And even for protocol providers, this would allow them to find out what are the constraints that are going to work with for various kind of networking and the storage problems. What are the capabilities of these servers? Where are they operating? And what are the capacities essentially for them? So for this purpose, what we provide is Edge for Cloud. And it's an all-inclusive cloud model that we tries to capture the requirements of majority of the applications that are utilizing the edge. As the name suggests, the Edge for Cloud is divided into three major layers. The first layer is the edge. Essentially, this is the outermost layer of this logical construction, where there is a collection of loosely coupled devices which are going to be crowdsourced. For example, your smartphones and your workstations and even your desktops can become part of this entire layer as volunteer resources. Why this layer is necessary and what kind of benefits it provides is because it's very close to the sensors and the clients, so the overall processing that is running on these devices, they might be very limited, but they kind of remove the networking latency problems that the data center was having. However, these devices, they are very heterogeneous in their nature, so they will be using your wireless, most of the time wireless connectivity to form ad hoc networks to get things going. The second layer is the fog, and this is where the cloud providers can come in. Essentially, they can deploy these specialized servers in this layer that form parts of the networking infrastructure, or even the existing cloud infrastructure, but in near the users as much as possible. The idea being that you can co-locate this with existing networking devices, for example, your routers and your base stations of the cellular providers. These devices have much higher processing capabilities than the edge. They also support the existing virtualized technologies that the cloud provides, so it's easier to run stuff on them, but they are not able to support the same low latency capabilities that the edge provides. The core of this entire edge fog model is the cloud, which we essentially make it as a data store. Essentially, the cloud is no longer capable of doing computations, it's only used for data archival and storage purposes. The reason why we're doing this is because most of these devices on the edge of the fog, they can have very limited storage capacities. So data store kind of provides them a reliable and ease of access storage, irrespective of their locations and their networking capacities, so that your computations that are running on this model essentially can run without any problems. So what are the salient benefits of this model? Obviously, it is a non-inclusive edge architecture, so we are not making any great demarcations between the requirements of the application providers and what we are providing here. Some of these servers, for example, at the edge, like smartphones and tablets, have an inherent support for mobility applications, which might be required for the autonomous vehicles, for example. And they try to satisfy, in fact, most of the emerging application requirements. The biggest point and the selling point of this architecture is that it's completely distributed in the way it works. So there is no single point of failures, and the processing should be able to get around with any failures that is happening over the networks. And essentially, there is not just a single vendor that is working on this logical model. So essentially, there's no vendor lock-in. So there can be a lot of managing entities that are working on this model. So now that we have a reference architecture, the next question that obviously comes up is how to utilize these heterogeneous set of resources that have different kind of processing requirements to the best of their capabilities. And that's what brings me to my next solution, which is the infrastructure layer. So before we get into how it works, we try to formalize what a task deployment or a job deployment on an H4 cloud would look like. And this is a snapshot for example purposes that I'm showing here. So it might, the H4 cloud might be composed of multiple applications. They might have different kind of requirements. They might have different kind of networking connectivity between them. Some of them might be connected through low latency Bluetooth connections. Some of them might have a direct Wi-Fi to Wi-Fi or via cellular connectivity. Some of them might even have a high bandwidth Ethernet connection between them. All of these connections essentially can be modeled as constraints. Each network connections can be modeled as, for example, the latency between the two devices or the packet errors that the devices are encountering, or essentially what is the bandwidth of the connection. Similarly, each of the device can also be can have some constraints. For example, what is the processing capacity of each device, or it might be connected to some external battery, or it might be connected to the main power lines, and that is also needs to be taken into account. So if we try to dumb down this model into a node-based architecture, this is what the model would essentially look like. Each of the device is labeled with the letter D. The circles that you see here can be your edge nodes. The rectangles, however, can be the fog nodes, which can be more processing capable. Every network link between these two devices essentially means that there is a direct connectivity between them, and the weight on the network link means that there is certain kind of constraint on this device, which can be different for who's running the application. So this can be modeled on the code. So now let's assume that there is an application that wants to utilize this edge-fork model. This application can be an autonomous vehicle, for example, and the application can be broken down into various sub-jobs. So here we are assuming that the sub-job is, there is a 1:1 mapping between the device and sub-jobs. And the job graph looks like on the right itself. So each of the sub-jobs essentially have these links, which are the dependency links, which means that any of these sub-jobs which have the link needs to communicate over the network to get the processing done. So devices who are running these sub-jobs with dependencies between them will be utilizing the network links. So the obvious question for task deployment, it can be that how do you best map this sub-job into this device graph jobs? And the de facto way of solving this in the literature is that you try to minimize the overall networking that is used for mapping these jobs to devices. This has certain problems, and let me explain you very briefly why. The device graph here that you show that can be modeled as a square matrix if you just look into the networks of the various links that exist between the devices. So every element in the matrix essentially means the shortest path between any of these two devices, right? Similarly, the job dependency graph can be modeled as the following square matrix, which is if there exists a link between any of these two devices itself. So now the question is that how do you minimize the product of these two square matrix? And in literature, it's shown that this problem is known to be NP hard, which means that it's the optimal solution for this problem is not guaranteed. And even just for reference purposes, for example, just for 30 nodes, for 30 device graph, it can take 2,500 servers to solve it, and even then the optimal solution might not come out. And that's a problem because when we are tackling edge-fork graphs which have a huge density of these devices over the network, you want to do things fast and you want to avoid this entire complexity. And this is where our solutions come in. So essentially what we provide is two different solutions that try to circumvent the entire problem of this exceeding problem search space which the NP-hard problems gets into. One is the least processing cost first, and the other one is the energy efficient variant of this least processing cost first. For the purpose of this presentation, I'll only explain how least processing cost is working. So the algorithm is very simple and it comes from the name itself. So rather than optimizing the networking, we are optimizing the processing cost first. And why we're doing that? The reason why we do that is because if you don't look at the networking links and you only look at the device processing capabilities, which is shown in the blue here, this matrix is a linear matrix. Similarly, every job can be modeled as the various processing requirements it has for getting this computation done right. And that itself also is a linear matrix. And if you try to find a deployment which is utilizing a product of both of these linear matrices, this is known as a linear assignment problem. And essentially this can be solved in polynomial time and the optimal solution is always guaranteed. for this problem. So this is good for us because we at least now have one deployment that matches your jobs on these devices, and we can do it very fast. There are multiple variants available that can even cut down these processing time much slower. But the problem now is, if you look at the deployments, it finds the least processing cost, but we have no idea whether this deployment has the least networking cost because we have not calculated that. And we have no option to calculate it because we have no other options to look into. So that's what we're doing in the second step of LPCF. What we're doing is we're generating options, and we are generating other deployments from this initial deployment. And for this, we are capturing the inherent property of the H4 cloud, that it may be composed of multiple homogeneous devices which have the same processing capabilities. Similarly, these jobs that are being deployed, they can be homogeneous jobs on these devices. So for now, we build up a search space, and how we're doing that, we look into the devices which have the same processing power, and we interchange the jobs on these devices. Similarly, the jobs which require the same kind of processing can be interchanged on the devices. So with that, we now have a set of other deployments. All of them will have the least processing cost that we initially calculated in the first step. But now we have options. In the third step, we don't optimize anything. We essentially iteratively find out what is the networking cost of each of these deployments, and we simply pick up the one with the least networking cost. So to quickly recap what LPCF is doing, it looks into a deployment, it calculates one with the least processing cost, and then it calculates a subgraph, and it finds out a networking cost which is almost optimal. We have no idea how optimal it is. So we try to find it out, how optimal it is. And we find out, the graph on the left essentially shows that. So if we are comparing it with the optimal solution, that is the blue curve, and we find out that we are always within the 10% range of the optimal solution, even if we are doing this search space, because we have a lot of set of devices which have the same kind of processing powers, and essentially we get a pretty significant problem search space to look into. This is good for us because if we look at the processing cost, we are doing multiple times better than what the de facto solution was doing, because it's not looking at the processing cost at all. The energy efficient variant of the LPCF, which I've not discussed here, but essentially what we are able to get with that, we are even able to get 10% reduction in overall energy used for doing this processing. And in fact, it is able to get more than 20% energy reduction in the edge layer itself, which is composed of battery constrained devices. So with that, this kind of summarizes the LPCF in the LPCF, how it works. The other protocols that I'm providing in the thesis also looks into various problems of the edge and tries to maximize the capabilities of the edge so that they're able to provide the best possible service requirements to the users. Most of these protocols are based on the following publications that I did in my Ph.D. And with that, I conclude my talk. Professor Abhishek, I now call upon you to give your critical comments on the presentation.